Hi everyone, this is Lun Lam. Welcome to the AIRS in the Air online activity. In this month, we will host a series of special talks on modular self-reconfigurable robots to help promote the knowledge sharing and technological advancement in this field. With the rapid development of robotics and AI technology, people's expectations for robots have gradually shifted from the previous special purpose to the general purpose. And modular self-reconfigurable robots are regarded as one of the most important directions for realizing general-purpose robots. Nowadays, this technology still faces many challenges in practical application, and whereas many scholars all over the world are making efforts in this field and have achieved remarkable results. Today, it is our honor to have two well-renowned scholars to share this topic with us. There will be a Q&A session after each of the talks, so you are more than welcome to interact with our speakers by leaving your question in the chat box or ask the question directly if you are using Zoom. Okay, I'm delighted to introduce our first speaker, Professor Mark Yim at UPenn, and he's got his PhD degree in 1994 from Stanford University, and he's now the Asher Whitney Professor of Mechanical Engineering in the School of Engineering and Applied Science. And he is the director of the GRAPS Lab, which is the oldest robotics research lab established in 1980s. And he has received many honors, includes the Linkback Award for Distinguished Teaching, which is UPenn's highest teaching honor, and induction to MIT TR 100 in 1999, induction to the National Academy of Inventors in 2018. His current research focus includes reconfigurable truss robots that can help in search and rescue operations, swarm of boats that can attach together and reconfigure their shape, swarm of small flying robots that can group into shape and interact with humans, and swarm of microscopic robots that can build structures. Professor Yim is a pioneer in modular self-reconfigurable robots. I very much appreciate that Professor Yim is agreed to share his wisdom in this event. And his topic in today, he is going to share the reconfigurable trusses, a space-efficient approach for modular self-reconfigurable robots. So without further delay, let's welcome Professor Yim.
Thank you, Dr. Lam. So yes, I'm going to talk about reconfigurable trusses, which are a space-efficient approach for modular self-configurable robots. But first, I'd like to talk a little bit about the GRASP Lab. Since I'm the director of the GRASP Lab, I need to just give a little bit of the background of where I'm coming from. The GRASP Lab, as Dr. Lam mentioned, is the oldest. At 40 years, we have around 130 PhD students and 180 master's students, about 20 faculty in a large variety of areas, including perception and machine learning and control planning and mechanisms. So that's me at the bottom. We've been around for 43 years, which is the oldest in the country. And I think that makes it the oldest in the world. I'm not positive, but that's currently where we are sitting. So today, what I'd like to do is talk briefly about modular self-reconfigurable robots that I've been doing in my lab over the past quarter century or so. And then I'll talk about this variable topology truss, which is the newer system that we're starting to look at that's more space efficient. First about the hardware and then the software. So what is a modular reconfigurable robot? Essentially, it's modules that are very simple and repeated. You have lots of them. You can combine them together to form larger shapes. They can reconfigure themselves into different shapes to do different things. So historically, Toshi Fukuda did this thing called the cellular robot or CBOT in 1989. That was his first publication. Now, if you go to Google Scholar and you search for reconfigurable robot, there are 97,000 papers that show up. So there's a lot. Self-reconfigurable robots is still in the thousands. So there are a lot of papers since then. There's a lot of people that have been looking at that. What can you do with them? This is a video from 20 years ago. Just showing, for example, you can have a robot that rolls like a loop that's fairly efficient, or can move like a snake that's better at moving through terrain, or go through small cluttered environments and that type of thing. The robot theoretically could also reconfigure itself, maybe into a legged configuration. Legged robots tend to be better at like stepping over uncertain terrain and that type of thing. So over the years, there are a lot of different types of robots. There's even a book now on self-reconfigurable robots that kind of is like a survey of the different robot types that have been created, modular self-reconfigurable robots. And in general, there are two main ones, I think. There's this one thing that we call the chain type, which is the one that you just saw the video of, in which the modules form serial chains that are like arms or legs. And then there's the lattice type, which are modules which are often cubes, but don't have to be cubes. They're usually space-filling geometric forms that attach together. And then there's the hybrids, which can do both lattice and chain type. But between the chain type and the lattice type, the chain type tends to be the types of robots that can do more things and be more useful, because you can form arms that can manipulate, or legs that can move or push on things. It tends to be more useful. The lattice ones tend to be more just forming shapes, structures, and reconfiguring into different structures. However, the lattice one tends to be more interesting in terms of programming, because it's actually typically easier to represent in an algorithm. And you can have distributed algorithms, or there are a lot of interesting things to look at. Very often in the chain type, we've only seen maybe dozens of modules in a single configuration, whereas the lattice type, people have built maybe hundreds, or simulated millions, even millions of modules. So their lattice types tend to have more activity, especially in the computer science area. The hybrid versions can reconfigure as the lattice, but also form chain style robots. And then there's another category that we call mobile, in which the individual modules are mobile in the environment. So in the year 2000, I wrote a paper in ICRA, the ICRA conference, in which I said there are three promises of modular self-reconfigurable robots. They can be versatile, because self-reconfigurable robots can change their shape to suit the tasks and changing environments. They can be robust, because they can, if there's some modules that are damaged, they can reconfigure themselves so that or they can throw away bad modules if you have redundancy, or they can self-repair theoretically. And they can be low cost. If you have lots of repeated modules, you can use economies of scale to reduce the cost of individual modules. Of course, this was promises, and I didn't know if they were true. This was 20 years ago. Essentially, versatility has borne out. Yes, we can do lots and lots of different things. The robustness one, I'm not so sure. Maybe we've got some examples. People are starting to make some progress towards robustness. The low cost one, I think, is pretty much not true. And certainly in some aspects, it's not true. And that's what I'm going to be talking about. And eventually it may become true, but I'm not sure. Okay, so let's talk about versatility. In terms of versatility, there are lots of different styles of locomotion that modular robots can do, different types of walking or rolling or moving like a snake. This is actually a video of we made a snake and actually put it inside like a little gopher hole in the ground to see with a camera in the hand, and explored the different types of things you can see. We actually used the concertina snake-like gate, which is an open loop gate that conforms to the shape of the tunnel, and that worked pretty well. These robots can also climbing poles, climbing fences, climbing stairs. There's lots of different types of mobility, and they can even use human vehicles like a bicycle or a tricycle and that type of thing. This last video is actually a video of I think the largest number of modules we had in a single configuration, which is about 55, 56 modules in a 14-legged centipede-like gait. So there are lots of different types of things you can do. I think we've shown there are maybe hundreds of different gaits that people have shown. People have also done manipulation, so lots of different types of manipulation. Essentially, I think the versatility has been shown. Robustness is another issue. When you have lots of modules, you have lots of more modules that can break, and so things are often failing. But here's a simple example from 15 years ago of a kind of a self-reassembly or kind of like a self-repair. So the robot's kind of walking by itself, and then some mean grad student comes up and kicks it into pieces. It can reassemble itself. So in this particular case, we've got groups of modules. I think there are 3 or 4 modules with a smart camera on board. The little blinking light actually is what the camera uses to communicate. Each little group can communicate with the others through the blinking light, and they can see that blinking light. They also have an accelerometer, so they can tell whether they're upside down or upside up. They have a self-righting behavior. And the first thing it does is go through a search pattern to find the other pieces. It recognizes that it's fallen apart, and so it tries to reassemble itself. And they can move kind of worms essentially around and try to reconnect. Each one of these groups have magnets on the side, so they can dock to each other with the magnets. I'm going to just speed up a little bit here, get toward the end. So the system can ultimately dock together, and then the idea is that if it ever falls apart, or if someone takes it apart, it can reassemble itself and then continue on the task that it was working on. In this particular case, the robot was walking, and this video that we took, something kind of funny happened at the end as it was standing up again. I think one of the legs or one of the feet got caught in the carpet, and as it tried to take its first step, it fell down and fell apart, which was unfortunate. But it kind of also, I think, an example of people kept thinking, oh gosh, robots are going to take over the world because they can repair themselves and you can never destroy them, or we can barely make them walk. So I don't think it's really a concern. Okay, so that was 15 years ago. Something that's a little bit more recent is a system that we call s'mores EP, whereas the previous system had individual modules that had 1 degree of freedom. These modules have 4 degrees of freedom. They have these connection plates. There are 4 of them, 3 round ones and 1 square one. The 3 round ones can rotate. Every face can be connected to every other face, so any module can connect to any other face. Each one of these faces can be connected at 90-degree rotations. So any 2 modules can attach in 17 different distinct kinematic ways at 90-degree intervals, or depending on where that square one attaches. Maybe it's most easy to see in the video. Here you can see the 2 side round faces can actually be used as wheels, so they can drive around by themselves, be individual. They can detach or attach through that electropermanent magnet. Modules by themselves can drive around, but they aren't necessarily so useful. They may come up to a crack and get stuck. Larger groups of modules can dock together and then increase their capability by doing things like being able to cross over gaps or other things. So this particular demo was actually done manually. There's a person who's driving each module, but we would like to have these things be autonomous. So one of the things in this particular publication from just a couple years ago was looking at how do we assign which module maps to a different module in a configuration, and then how can we get them to assemble themselves. We've done in previous work, 1 module at a time can dock. This one is multiple modules assembling at the same time. And so this is just an example of self-assembly for an arbitrary configuration. In this case is what we call a mobile manipulator. It has a longer series of modules that can act like an arm. the docking is done in a Vicon motion capture system. So the modules know where they are through the motion capture system, and they use that to dock. They all do have motion planning that are all standard things, and you can do a variety of different shapes. So that's a more recent version of modular reconfigurable robot that we have. So the third promise was cost. And the one thing that, so just looking at cost, the very early modules that I showed from the ones like 20 years ago, they were about $100 per module, about 5 centimeters on the side. We had a later version that was about $3,000, just to give you an idea of the range of costs. The S'mores EP that I just showed you from just now, the more recent ones, they're also about $100. Of course, there's actually a huge amount of labor. The magnets are, we had graduate students actually wrap the wires and machine out the pulp pieces for hundreds of magnets that are in each module. There's lots and lots of parts. So there's a ton of labor. So $100 actually is not exactly right if you include the labor involved. But in any case, it's around on the order of hundreds. It would be useful to look at the scaling idea though. Kilobots, which is Michael Rubenstein and a bunch of others built, that was about $14 in parts for 1,000. It was very limited what it can do though. They kind of vibrated and moved around that way, and they were about 3 centimeters in diameter. Also, if you look at millions of elements, Ed Steger, Vijay Kumar, and others looked at using bacteria. So you got millions of bacteria swimming around. Can you get them to push microscopic objects around and do that type of interesting thing in terms of swarm robots? And for about $16, you can get a vial of bacteria that's about 5 milliliters. So the number of modules is actually not that appropriate, depending on the size of the task that you want to have done. So if you've got a task in which you need, like a human-sized person, you need something about that big. And it doesn't scale that well with the numbers. Like if you were to do it with bacteria, you're going to need trillions. I mean, still $16 is millions of them, but they're super tiny. So it doesn't really make sense. The costs, when you think about size for modular robots, just doesn't necessarily scale so well, at least with all the modules that we have so far. So that brings us to the variable topology truss. This is a system that does scale well with size, and that's because it can change its size. And so I'd like to talk a bit about that. So the inspiration for this variable topology truss started with this thing that came from NASA Goddard in 2005, 17 years ago. Essentially, it's a truss in which the members can change length, the truss members, each one of these rods. And of course, this is a simulation of what might look like, this robot exploring Mars or something. It can do things like chimneying up cracks. Also, in the very beginning, you saw it started out very small and then expanded to a much larger size. It can roll around in this fashion, kind of changing its center of mass, maybe crossover gaps and that type of thing. So there was actually an earlier piece of work that was looking at variable length trusses. And this was the work of Hamlin and Sanderson. And this is actually predated the NASA work. This is 1997. This is something that's called tetrabot. I don't have a better picture, unfortunately. But each one of these members can change their length. They didn't change very much. The extension to compression ratio was not more than maybe 2, whereas the simulated video you saw there was probably 100. But it actually was, and then they had these node mechanisms, which are actually very important and very interesting. And we actually borrow some of that ideas in our work as well. And I'll go a little bit more detail on that. So this is what we envision the variable topology truss to look like. The robot can roll around just like on the other one. And the application we're looking at was search and rescue. And in particular, in a damaged area, one of the things that the rescuers need to do is shore up a building to make sure that the building doesn't fall on them as they look for victims. So that was our ultimate goal. The one difference between all the previous work and this one is that the truss topology can change. And so this isn't actually the way that we ultimately got our topology to change, but an example of how, if you have a different topology, you can form different shapes, which actually very often is very critical to making the shape. Like if you wanted to have a large tower that could do things like lift up a building, you'd have to change the topology from the one that was run before. Okay, so what do you need to have a system that can shore a building? So that holding up a building that's damaged is called shoring the building. It needs to be very, very strong to support thousands of pounds and have a very large reach. And so that's where trusses come in. Trusses are naturally used everywhere in any type of building that you see. And that's because it's strong and very efficient materially and therefore cost to make a larger structure that's also strong. So trusses are the natural thing to use in terms of an engineering technology. So this is our one of the latest versions of our VTT, or variable topology truss. So you can see the elements, the members can change their length, and also the joints between them are using the same type of structure that the Hanlon and Sanderson Tetrabot uses. So the members that change their length are basically based on what we call the spiral zipper, which is a prismatic joint. And essentially it's a band, in this case, we're just using a plastic band that can form a tube. And it's like a zipper in the sense that there's what's called the slider on the zipper, the bottom part that joins together the top part of a band with the bottom part of the band. It has a certain teeth pattern. And therefore you can essentially zipper together a band into a tube. The nice thing about the tube is that it's very strong. It's naturally light and strong, and I believe it's the optimal shape for making strength to weight ratio in terms of under compression. In our VTT, we have what we call an edge module. So the edge module is composed of the spiral zipper in the middle, and then the two ends are what we call the node ends. And this is a simple example test that we have in a VTT structure as we are examining, just to make sure that the extension and compression is working properly. So in trusses, the smallest truss you can have is a tetrahedron, which is the 6 members with 4 nodes. A characteristic of a truss normally is that you want the truss to be statically determinate, not over constrained or under constrained. If it's under constrained, you're going to have parts that flop around, and so it's not controllable. Over constrained means that you might have moments that are can cause stresses if you have errors in length. So often, if you look at bridges, they won't have all of the points that the bridges are attached planted in the ground. They'll actually have rollers on some parts. And that's because very often in bridges, you want them to be statically determined. You don't want to be over-determined if they stretch due to temperature and that type of thing. So in our case, we're going to use the nodes as spherical joints. What we want is for the nodes to locate the position, but not constrain the angle of the truss members. In the truss members, we want to have very high expansion to compression ratio, so the spiral zipper gives us that. The other thing that we want with our nodes is to allow the systems to have their topology change, and for that we need the nodes to have arbitrary degrees, an arbitrary number of members that are attached at that point, which makes the design actually quite difficult. The way to do that, one way to do that is to make them chainable. So chainable means that you can attach more members onto the end of a chain. And that way you can grow or merge or have larger nodes of arbitrary degree. Also, we want to make things as simple as possible, which is always a design goal. So here's a snapshot from that NASA Goddard robot. And there are a couple things that make it not really feasible or realistic. One thing is that they're collapsed really small. The angles are really tight, and very likely it's going to collide with each other. These tubes must have some diameter, and they're actual physical objects, not just drawings. And so they take space, and so you'll get some collision, and that causes an issue. The expansion to compression ratio was very, very large, maybe larger than is feasible, and maybe as far as I can imagine. And then the other thing is motion planning. You know, they had, I think, 18 members, so that's 18 degrees of freedom, which is kind of difficult. So here's an example of chaining we have. So if this is a node, and the members come on here, there's a yellow member, blue member, and a red member. This forms a chain, but the blue and the red are free, or they're open. So this is where we can attach another member if we wanted to add more members to it. So this would be one node here, and the way that we would be able to change the topology is by adding more members to a node that way. We got an extension ratio about 45 to 1. In practice, we haven't needed to go that large, but I imagine we'd start to run into some strength issues as well, just because it is very, very large. The minimum angle we got between two members was about 20 degrees. It looks like they got to 5 in this video, which is, you know, very, very difficult. So the way we do merging, I mean, reconfiguration is what we call merging and splitting. Essentially, if you have members that have 6 members or more, they can split apart and then rejoin. And so splitting and merging is this part. Again, using that chainable method is what we're talking about. So anytime you need to have at least 3 members to be controllable. And then, if you have 6 or more, you can split in different ways. So if you had a cube that you wanted to make into that tower, like we did, like in that original video, you might start with these 2 nodes and have them merge together. So they might bend down first here, and then join, and then split. When it splits apart in a different way than it was in this case. And so then you can configure into this larger configuration there. So what does it mean for a physical thing to join and split? This shows how, just a quick video. You can see how these 2 are originally this way with these 3, and then those 3 off to the side. Here, Alexander is showing what that thing looks like. Let me just show this again. This is how they dock. 2 things would dock together from one to the next, and then this little brass piece comes in to lock it in, and then you can then rotate around the node, so it's free to rotate, but is constrained in position, and it undocks by moving that piece down. Okay, so that's kind of a quick recap of, or a quick overview of the hardware elements, which are primarily the members and the nodes. I'd like to now talk a little bit about the configuration analysis and reconfiguration. So the software basically breaks up into 2 parts. Because we can change the configuration of the topology, the reconfiguration planning is one thing that we need to think about. We haven't really solved that part yet. So I can tell you a little bit more about where we are on that. And then there's the motion planning. We have, 18 degrees of freedom or more. How can we do motion planning for that? And a lot depends on the geometry. So the nice thing about a truss is that it can be represented as a graph. It's very convenient. Graphs are, graph analysis and all that type of algorithms. There are many, many algorithms for doing stuff with graphs and manipulating graphs. Essentially, every truss member can be an edge in the graph, and every node can be a vertex. The problem is that we have a physical system, and graphs in general don't always keep all the constraints that you have with a normal physical system. The other thing is that so there's the connectivity. If you have physical nodes, where they are in a graph matters. Even if they are exactly the same graph visually, these 2 are exactly the same, but they have different connectivities, or you can consider it labelings. They have different labelings. All 3 graphs are the same topology, 4 nodes with 5 members between them. These 2 have the same connectivity, but it's a different configuration. It's a different shape. So how do we deal with it? That's one thing. graphs don't necessarily preserve the number of members or the number of edges. The number of edges can change as you do manipulations on the graph. In our case, the number of members must be the same. The number of nodes can change because we can merge nodes or split nodes, but the number of members are physical tubes that can't disappear or be created out of thin air. The other thing is that the nodes have to be degree 3 or larger in order to mean controllability. And then there's this thing about rigidity. That's a little bit doing analysis for being statically stable and maintaining rigidity is another concern. Then there are the other physical constraints, the minimum angle I mentioned before. Members can't be infinitely long. And then there's looking at singularities in the configuration for motion as well as self-collision. Self-collision is actually one of the biggest ones, which we'll talk about in a minute. So another thing that's a little bit not quite so intuitive is, so this is a simple 2D example of a graph in which we might want to merge these two nodes. If we merge these two nodes, these two members would have to bend, in order to not collide. You'd have to have curves in order to not collide. And in reality, if you do just graph manipulation, these two would merge and this member would disappear, which can't happen. You can't just make it disappear. So what you need to do is have this one that's connected to it be two members, and then these two can merge together without having these two guys disappear. So if any two nodes want to merge, they can't have a shared member. Okay, so that's one constraint. We can look at this one. Let's say here's a tetrahedron. Can we do any merging or splitting with the tetrahedron, which is the minimum number of members? And we can't. Like if this member and this member were to merge together, this node and this node, this vertical member would become zero length, which it can't do. It can't become zero length. It's a physical tube. It can get smaller, but we can't get zero. Okay, here's an octahedron. This has 12 members. Can this one reconfigure or merge and split? And it turns out it can't. Again, this one can dock with these two opposing ones without having any member turn to zero length, but these two side members would again have that problem where they would merge, the tubes would merge, and so that can't work either. It needs to be bigger. And it turns out that if you do the analysis, we have a proof that you actually need to have at least 18 members. So this is a 21 member, and these two things can merge together. So that's a lot. That means that every robot has at least 18 degrees of freedom. And if you do any planning, you have an 18-dimensional space at a minimum, which is kind of a lot. So one of the things that we start to look at when you look at the topology is topology neighbor graph. So this is the work of Alexander Spinos. Each one of these circles, little red circles, represents a particular topology. And when you have a splitting or a merging, that moves to a connected, every time you merge, you move to a neighboring, that edge represents either a split or a merge action. And by doing that, all of these configurations are then thus connected by sequence of merges and splits. And this is how you can kind of get from one configuration into another configuration. So here's a list of 6 different configurations that we actually figured are kind of useful. This one is really compact. This one is what we call the wall shore. If you need to shore a wall from falling down, the ground would be here, the wall is here. This is a tower, or what we call a ceiling shore. This could be a tent or a cube. This one, which we call the quadruped, turns out to be not connected. Even though it's the same number of nodes and members, or at least the same number of members, not necessarily the same number of nodes, there is no way to get this topology through a sequence of splits and merges from these other ones. So it would have to be a separate version. So the path planning at the topology level is doing this. What is the sequence of merges and splits that you'll need to get from one arbitrary configuration to another arbitrary configuration? And ideally, you'd want to do that in the shortest number of steps. So that's the topology level path planning, which is the hardest part, is just initially enumerating and finding out, are they in the same connected component? When you have 18 members, actually the number of configurations aren't that large. But once you get to 21, 24, 27, it grows exponentially into many, many millions or billions. So some of the latest work that we actually have that Alexander's been working on is actually looking at the same configuration. Even if you have a goal and a starting topology or configuration, are they the same? Can they be, or can you relabel them so that they are the same? And that's a question that's even not necessarily easy to use. And so he uses a link knot theory, and looking at link invariance, you can actually analyze and see, can they be reconfigured to or rearranged without having to reconfigure and detach or reattach them. And so this is an example using the analysis. This particular start configuration can be this goal configuration through some rotations and relabeling and moving a little bit. It ends up that this one is the same as that one, but you have to relabel it slightly. So this is a paper that's actually coming out in ICRA. That's happening here in Philadelphia in a couple of weeks. So hopefully you'll be here and you can talk to Alexander about this work. I'm not going to go into more detail about that. Okay, the second half of the software part is looking at motion planning. So as I mentioned, we need at least 18 members, at least 18 degrees of freedom. So it's at least 18 dimensional space. The biggest problem is that these tubes are fairly close together. And so the configuration space, self-collision is the thing that we're most worried about. And it happens a lot because they're all kind of intertwined with each other. So even a simple motion of going from the cube into this tower is not that straightforward. So this was done using a randomized path planning technique, and it took hours to solve. It was slow because it's a big, it's a big space. So it's not an easy thing. One of the things, we came up with a better way, actually Chao Lu came up with a better way of doing this. If you look at, let's just look at the free space of a single node. So in this particular case, this guy in the middle, where can it move without self-colliding? Pretty clearly, it can move anywhere inside the cube that it starts with, but it can also move outside of each one of these faces. And so this yellow structure represents what the free space is of this particular node in the way that it can move without colliding. The limit, these polyhedron actually extend to infinity if the tubes can extend to infinity. The limit of this size is just the joint limits of the tubes. And so that's why they're kind of close up in this size. But so this is the free space. The question is, how do we generate this collision-free space for this one particular node? And it turns out that you can relatively easily generate it, and it's essentially every node. You need to think about the motions of nodes, not the changing of members. So if you think about this node moving and its possible intersections with this bar, the polygon that the triangle forms a half space. On this half of the polygon, this bar that's connected to it would collide with this, and it would be free on the other half space. The other bars, it would be vice versa. So these polygons form the boundaries of the space. So if you basically take all possible polygons that are generated from this type of interaction, and you take the intersection of where all of these polygons are connected together, where they form polyhedron, you end up with, and then you can actually determine which ones form the free space for the node that you're in particular looking at. And this can be done in polynomial time. Essentially, it's on the order of the number of members to the fourth power. So it's polynomial. Once you do that, motion planning for an individual node is relatively straightforward. We can take convert each one of, this is a convex polyhedron, so you can convert it into a it's convex, so we can turn, concave, we can turn the convex sequence of convex polyhedron, and then just do a simple, let's say we want to move from this position to this position. You're just moving through the convex polyhedron sequentially. So it's basically a cell decomposition standard motion planning technique. So it's deterministic, it's complete, and it's fast, so it works pretty well. But the one thing is that it's only for one module moving at a time. So it's very different from the first example that I showed where they're all moving at the same time using the randomized path planning technique. So if we started with this cube, and again, we wanted to form this tower, this essentially shows an animation of how it could be done. This one was solved in 4 seconds, much, much faster than the planning technique, the randomized path planning technique, but it's only moving one at a time. Essentially what we do is we just can look at each one of the members, each one of the nodes that needs to be moved, and then searching through the possible order, finding the sequence of which ones need to move when in order to get it to the final configuration. The one issue with this is that we are not guaranteed to find a solution even if one does need to. If multiple modules must be moved at the same time, I mean multiple nodes, it's possible that we won't find a solution even when one does exist. But so the other ones would work. It's just the other method would work. If you did, it's just much slower. So obviously you could do this quickly first, while if you actually need to find something complete and using, well, the randomized path planning method isn't complete either. But in any case, they end up with different solutions. Ours is just very fast. So here's another kind of fun planning aspect. And so this isn't actually planning, reconfiguration planning or motion planning, but it's more local motion planning. So since we have a robot that can essentially change its size, if we had a environment in which there were small obstacles in which we needed to go through, small gaps, the robot could change its size in order to go through them. So this is the locomotion planning for the VTT in an octahedron shape using the kind of rolling or tumbling type of gates. It uses the random tree methods to find the path. The difference here is there are a couple differences. One is that it's applied to specifically center of mass rolling. This little pink part is the center of mass as it rolls to the different faces. But the fun thing is that when it comes up to the small gap, it can just change its size, and theoretically, depending on how small it can get through smaller, the small as a gap as it can get itself. Okay, so the latest version that we have that's moving towards that locomotion is now getting with this is it tends to speed it up, but essentially taking steps this way, moving one over at a time. I actually want to mention one thing as I'm nearing the end here. As we are doing the development of these systems, one of the things that we are realizing is that many times you need lots and lots of modules, and you're doing lots of things at the same time. You're developing new modules, you're redesigning them, you're doing experiments with them, with the software, as well as doing demonstrations. So you essentially want as many modules as you can have because you want to push the types of software control problems that you have. Usually they're looking at what you can do with large numbers of modules, but at the same time, those things are breaking because you're developing them and you're experimenting with them. So you need extras. And one of the things that we realize that we often use the older designs even as we make new ones. And so it's kind of critical that you have the same standard interface as you use the older designs because you're constantly pushing the number of modules that you have. So just to give you an example of, this is a typical experiment that we have. It is unfortunate. And the sad thing is that this video we have many, many more videos like this than the previous one where they're successful. But that's, the typical thing with development. So this has been the work of many people at Penn and many people in Seoul National University. We had a joint project at Seoul National University with Jungwon Kim and Frank Park and Taewon Saw as co-PIs. This is a quick list of the publications in case anyone, I'm just going to flash this up here for anyone to see. Here's a picture of the group, and I'm happy to take your questions.
Okay, thank you very much, Professor Yim, for the excellent talk. And one thing that amazed me a lot is the expansion ratio of the truss member. I think the mechanical design is very genius. It can have a very compact at the beginning, and it can make a very long rod by this structure. So, all right. So, is there any questions so far for to ask Professor Mark Yim? It is a very valuable opportunity to interact with our guest speaker. Okay, I already saw some questions in the chat room. One of the questions, yes, yeah, can.
So do you want me to read it? It's quite long.
Yeah, it's quite long, but let me see. Maybe I can read it. Dear Professor Yim, thank you very much for sharing. Could you share your thought on configurations lesson? The modular self-reconfigurable robots can choose an appropriate configuration according to the environment and task. But how do we evaluate whether this configuration is appropriate for current environment and task? How do we choose the best configuration for current environment and task from exponentially growth configuration space? The deep learning and reinforcement learning holds any promise to solve this problem? Your guidance is great, appreciate. Yeah.
Okay, that's a really great question. Selecting the task or selecting the right configuration for a given task is really hard. It's one of the things that we have been looking at for a while. Maybe 10 years ago, I kept proposing this as a thesis direction for incoming students, and no one would take it because it's quite hard. At least in the most general. So the first question you have to ask is, how do you evaluate what a task is and break the task down into components so then you can compare it to a given capability of a robot. And in the most general case, you can imagine a task for a robot is usually applying forces in different locations in the environment. So what does that mean? Usually we don't normally think about that. Like if you're just holding an object in your hand, you're applying forces, but there are a lot of passive things you don't think about, keeping it stable or working against gravity, all the type of things you don't normally have to think about. And so there are a lot of simple things you can do. But if you think about, all of those forces and break it down, you can now analyze those forces, figure out, okay, how do you get a robot to apply forces in different locations? So I think the VTT, the variable topology truss, may be one of the most versatile types of systems because it has the ability to apply forces over large, areas in different ways without requiring a huge number of degrees of freedom and long ranges of motion. But I think it's really hard. We have started to look at the initial thing is what we've done is constrained the problem into tasks. Okay, here are a set of tasks. How do we choose which configuration? We have a set of configurations that can do a set of tasks. How do we just do a matching between those? That's easier. We tried to come up with methods like crowdsourcing large amounts of tasks, large amounts of configurations, and then thus tasks, and then seeing how they match. The thing that you can also do is what's called retargeting. If you have a given configuration that can often do things that other config doesn't have to match exactly one-to-one with a given config or with a given task. So very often people do that with humans. You have a human doing something and you want a robot to do the same thing. The robot doesn't have the same number of degrees of freedom as a human, but it can kind of mimic most of what the person does, at least the end effector. So that's one way that you can get closer to solving that problem.
Okay, thank you, Professor Yim. And the next questions come from our next speaker, Professor Kirstin Petersen. Yeah, then her question is, do you also foresee applications on the small scale that these robots could work well for?
Okay. Well, first of all, Professor Petersen, it's nice to see you. The small scale is always interesting. For this type of robot, I would really like to see if we can make them smaller. It's just the hardware design is super hard. And we've been looking at how to make things smaller, but it's, I mean, getting it to be smaller than, you know, meters is still difficult. Sub-centimeter is, it's just really hard. I think if we could do things, the thing is that this type of approach, I think, is very, very versatile because it can change the size and can move things around to apply forces in directions that most systems don't normally do. I think it would be really, really versatile. And so yes, if you can make it smaller, I think it would be great.
All right, thank you, Professor Yim. And the next question is, what is the most difficult challenge to generalize modular configurable robots to general heterogeneous multi-robot system? How to solve such challenge?
All right, that's an interesting question. Sometimes when you think about homogeneous, okay, so there's a very high level issue, where if you have a self-reconfigurable system that's made of homogeneous parts that can reconfigure and do lots of different things because it can reconfigure, it will never be as efficient as a heterogeneous or a specifically made system. You have a system that you have a task, and you make a system to do just that task. Because it's constrained to only do that task, you can make it optimal. You can make it cheaper, you can make it perform better, you can do all these types of things. When you have a homogeneous system that can reconfigure, because you have all of these other constraints that you want to do more tasks, it cannot be, if you're lucky, it can be just as optimal. Very likely it's going to be very, very suboptimal compared to the other one. So that's kind of very high level thing. When you compare heterogeneous to homogeneous, the more types of things that it can do, the less optimal it can be because of the nature of the problem. The most difficult challenge to generalize modular robots is kind of an interesting one. It's hard to say. One of the natural things about the problem is that it's very hardware and software. It's got problems in both at the same time. When you make changes in software and when you make changes in hardware, that makes the software more difficult. The software problems, because of its nature, are very difficult as well. One of the approaches that I keep saying we should try to do is make the software problem easier. Do the hardware, make the hardware more complicated if it makes the software system easier. Normally, that's not the way people usually think. Usually, you build a robot, you make the thing, and then you throw it to the software people, and then they program it. It's their problem at this point. That's the natural way. And this is kind of the reverse, and we haven't been able to do it. It's difficult because there's so much of a co-design problem. I think Professor Petersen may talk more about this. She does the same type of thing. But so what is the most difficult challenge is to generalize. That's a tricky problem because it's generalization usually means you have software that can handle things, but you also want the hardware to be, be able to do more at the same time. So I'm not sure how to answer that. It's kind of all at the same time. Maybe that's the problem, is that there's so many things you're trying to solve at the same time. Maybe that leads to machine learning or something like that.
Okay, thank you, Professor Maki. And is there any questions? Because we have a little bit overrun, so we may accept one more questions.
Hello, Professor Lim. Can you hear me?
Okay, good. Go ahead.
Thank you for a wonderful talk. Your team's work is eye-catching as always. Here I have a few questions and ideas about modular robotics, and I would like to hear your views. You just mentioned that the docking and UVTT is a challenge. Here I would like to share an idea which maybe work for docking UVTT. I'm a PhD student supervised by Professor Lam, and our group was on freeform modular robots. Recently we published a new modular robot Maybe I can turn on the video. Can you hear me? Yeah. Recently, we published a new modular robot. Here is the prototype. The docking in this system is, I think, it's quite similar to the docking between truss member and the node in VTT. You can understand the end of the truss is a card with the magnet, and the node is an iron sphere. The magnet can attract the sphere, and the card can move along the spherical surface of the sphere. So this design form a spherical drive between the truss member and the node. Okay, do you get the picture? I'm not sure, but I feel such design may be helpful in the VTT docking.
Yeah, so this is great. We are working on what we call VTT2, which we have not published yet, but we are taking very similar approach. So yeah, I think that's a very good idea.
Okay, just an idea for your reference, how we can help. If you're interested in our design, maybe we can share the link with you afterwards. Next are two questions for about modular robotics. Undoubtedly, you're an expert in this field, and I'm interested in your views on these questions. As I just mentioned, our group was on freeform modular robots. We came up with several freeform robots using magnets and AIRS spheres to achieve free connection among modules. You know the bucketball, right? Our goal is to achieve a flexible and freeform modular robotic system by mimicking the freeform connection between the bucketball. Professor Im, as an experienced scholar in the field of modular robotics, what do you think of our freeform robotics project? Do you have any suggestion or expectation on that? Thank you.
So it's difficult to see or understand from what you just said. Maybe we should connect later. I would certainly love to talk more about that. So definitely send me an email. We will let's connect later.
Okay. Thank you, Professor Matthew.
Can you hear me?
You still have questions to ask?
Hello?
I think there's one.
I have final question. One more question.
Okay,
yes, as you just mentioned, the lattice type, tray type, and multiply are the most mainstream categories. Most consensual classification in the modular robotics area today. However, over the past 20 years, the hardware of modular robotics keep developing. And it seems that some of the newborn modular robots seem unable to find their place in such a classification. I noticed that some scholars propose some new classifications. They include the new design as a new type alongside lattice type, tray type, and hybrid type. I once saw a survey paper claiming that there are 6 types of MSR, but I don't feel they're elegant. Professor Im, how do you see this classification of modular robotics? Do you have a more general classification for modular robots? Thanks.
So I didn't go into too much detail on the 3 types that I talked about at the beginning. I have had, I started with 3 and then 4 and then 5. The original 3 was based on the self-reconfiguration mechanism. So the chain type was if there are robots that make and break loops, then that would be classified as the chain type. If there are ones that sit nominally on a lattice and move around on a lattice, that would be the lattice type. And the third one was this mobile environment. Anything that uses the environment to reconfigure, to move around on before docking would be the mobile environment. So it's based on the reconfiguration mechanism. By that rule, the VTT truss robot is classified as a chain style because the splitting and merging is actually forming and making and breaking loops. But I kind of, in the end, I said, no, actually, it's so different from the others. I would actually classify it as its own truss robot style. And there are others. Stanford has another version, and I think there's another one as well that are kind of similar. So that's starting to be a class in and of itself. So classification systems are a little bit tricky. Very often you end up with miscellaneous or things that don't fit in, which is not great. It's not very elegant in terms of a classification system. But usually when you have a classification system, the value of it is in what you can say that about each that differentiates one from the next. And that's kind of where the lattice system is very different, because the approaches for algorithms are very different than the ones from the chain style. So maybe it's just lattice style and everybody else is maybe one way to think about it.
Okay, thank you very much. Although there are lots of questions live in the chat room, but I think it's time to stop the Q&A session, because later on we will have another speaker here. So let's thank Professor Yim again for his excellent sharing. And I believe our audience have gained a lot, especially in the Q&A session for the interaction. So let's thank Professor Yim. Thank you. Okay,
Thanks.
So yeah. All right, so let's move to the next part. And I'm so excited to introduce our second speaker, Professor Kirstin Petersen. Kirstin Petersen, yeah, hi, how are you? Yeah, and Kirstin Petersen is an assistant professor in the School of Electrical and Computer Engineering at Cornell University. She did her postdoc at Max Planck Institute for Intelligent Systems and her PhD at Harvard University and the Wyss Institute for Biological Inspired Engineering. Her graduate work features in and on the cover of Science, which is about a swarm of robots that can climb and place bricks to build a structure, which you can see. Yeah, and this idea is actually inspired me a lot for thinking if it is possible to make a robot to climb on other robots to achieve some self-reconfigurations. Yeah, and she was elected among the top 25 women to know in robotics by RoboHub in 2018 and received the Packard Fellowship in Science and Engineering in 2019 and the NFC Careers Award in 2021. Her lab is focused on design and coordination of robots cognitive, able to achieve complex behaviors beyond the reach of individuals, and corresponding study on how social insects do so in nature. Today, she is going to share with us her latest work, which is about the deformable modular robots. All right, without further delays, let's welcome Professor Kirstin Petersen.
Thank you so much for the kind introduction. It's hard to follow one of the forefathers of modular robots, but I'll try to navigate it carefully by focusing on a very different aspect of modular robots. And if there are any contradictions between what Professor Yim said and what I said, you should go with what he said. So I run the Collective Embodied Intelligence Lab at Cornell University, and what we do is really try to design and build and operate robot collectives that are inspired by swarms in nature. And so we look at a variety of mechanisms and materials, from like rigid robots, let me see if I can find my laser pointer here. So rigid robots to soft robots and even sort of natural swarms, because they all represent very different trade-offs when it comes to embodied intelligence. But today, the topic is not going to be on general swarms. It's going to be on these modular robots, and specifically deformable modular robots. And so, as Professor Yim has already said, right, like modular robots are basically composed of these active modules that can rearrange their connection topology often, and then try to adapt to dynamic environments or changing task settings or partial failures. And so my plan for today is to start by discussing what system intelligence means. It's going to start at a very high level. So what does system intelligence mean in these types of systems, where it's really spread across many agents that all physically interact, and they can occupy and potentially even operate on the same environment. And then, we'll sort of talk about the advantages of this design space between soft robots and robot collectives. And then we'll discuss the overall design philosophy that we tend to take in my lab. And then finally, I'll show you these 3 different systems down here that highlight some of those ideas that I'm going to present and represent different ways in which agents can really coordinate with each other. So I'm going to keep it fairly high level, but if you have any questions about particular details, please do ask. Okay, so let's start with system intelligence. So I'm just going to start by listing sort of different ways in which you can inject intelligence into robot collectives, because they're not all intuitive. Right, and please be lenient with my choice of words here. As I said, this is a very interdisciplinary talk, so the terms differ by the particular disciplines, and I'm just going to keep some that are fairly general in style. But basically, we know that if we want to generate an intelligent system, right, we can inject some amount of explicit intelligence, right? Software. We're comfortable with that type of development. And of course, if we have many robots working together, then we can either leverage sort of careful pre-planning, or if we have a dynamic task setting, we can add a centralized controller with overall communication. Or if we want to make our system a little more scalable and error tolerant, then we can do, distributed control with explicit agent-to-agent communication. But my point is that we can do more than that, right? So it turns out we can outsource quite a bit of that explicit intelligence to mechanical or morphological intelligence. So reflex-like behaviors that are built into the body of the robots here. And in nature, this concept often goes under this term of form and function, right? So the idea that every individual organism is optimized for the particular environment that exists in. And the same is true for coordination between agents, not just within the agents, but also between agents, right? They don't have to be explicit or even high bandwidth. They can be direct physical interactions or perturbations, if you will, between agents that work in the same environment. And they can be environmentally mediated interactions, right? So one robot can modify its environment, leaving a particular cue that then causes a robot which passes by later to commit a particular action. And so I would say sort of as a field, we're very comfortable with these types of design techniques. We're getting much better at large-scale communication networks. But systems based on all of these techniques over here, right, are still much more under development. And so in my lab, we really sort of try to look at the interplay between all of these different design techniques to generate task-oriented behavior in robot collectives or in modular robots for that matter. And part of that work really means sort of trying to develop very simple robots that can realistically be used in large collectives. And part of it is like figuring out new ways of generating both sort of scalable and robust coordination among those robots. And that's often done through studies of social insects. But today, we're just going to stick to one type of robot, right? These deformable modular robots. And they're really inspired by systems in nature. So let me give you a couple of examples, and there are many, but here's just 2 examples. So this first blob here is Visarum. It's a single cell slime mold. So this is a single cell. This entire blob can grow up to like 30 centimeters in diameter. Lots of nuclei inside of it, but there are no neurons at all. Right? It's all morphological intelligence, if you will. It moves and it grows through these periodic contractile motions that push fluids and nutrients back and forth inside of its membrane. You might have seen them, right? They've been pretty popular in the media lately for their ability to like connect pathways between multiple food sources hidden in mazes. And the cool thing is that I think organisms like this sort of hinted ways in which we can use advances in soft robots to produce these sort of individual mobile robots. It's a weird type of mobility, but it is mobility, with behavior-based like intelligence that's distributed throughout the morphology of the robot. And if we have robots like this, then we could have many of them working in close vicinity. And of course, there are collective versions as well. So here on the right, I'm showing you Dictyostelium discoidum, which is a social slime mold. So this is just an individual cell. But it's moving around, it's feeding on agar, it's quite versatile. But when there's dearth, many of those can come together, so hundreds of thousands of these can come together to form much bigger snake-like creatures that move through these coupled oscillations and coordinated cell contractions. And if you starve them long enough, they'll even morph into this fruiting body with a stalk made of dead cells and spores that fly off and repopulate new areas. There's incredibly sophisticated behaviors from these incredibly simple single-celled creatures. And I'm really excited about this idea of like robotic systems that could become as robust and versatile as these slime mold, right? Where we start with super simple individuals, but we have enough of them. And there's enough compliance in how they interact such that eventually they can generate this kind of emergent overall complexity. So really excited about this intersection of soft robots and robot swarms. And I want to talk a little bit about what that means next. So I'm going to give a brief motivation for why you should bother with many robots, and then why you should bother with soft robots, and then why those 2 fields really complement each other well. So I'm going to answer this question first. It's a very practical question, right? Like, why do you bother building more than one module or more than one robot when building a single robot well is already really, really hard, right? And I'm going to motivate my answer with this abstract graphical example from a recent paper of ours. So here you see two chiral swarmulators. So a chiral swarmulator is just a particle that rotates around some point. It has a phase related to where it is on that circular trajectory. And it has some spatial attraction to the other particles in the space. And two don't do much, right? They're not that exciting, but when you scale up the numbers, the swarm exhibits much more complex behaviors. And we can superimpose different means of coordination, right? So here we added phase coupling. We can even play around with the swarm composition. So here we added different natural frequencies. And we can produce a wealth of emergent behaviors that are much beyond what the individuals can achieve, right? Individuals still just have like the spatial attraction and phase coupling. That's all they do. But we can get like a huge wealth of emergent behaviors. And it's kind of interesting to think about, right? We start with these super simple particles where we can use first principles to analyze their behavior. But then as soon as we scale to larger numbers, their interaction produces these emergent behaviors that are incredibly complex to both predict and analyze. And so what I'm really hoping to show, right, and the answer to this question is sort of a quote from Aristotle, which is that we can try to achieve more than the sum of the parts. So by adding more modules, we're not just adding linearly more functionality, we're like actually creating a wealth of emergent behaviors or potential for a wealth of emergent behaviors. And if we make this a little more concrete, I think about modular robots, right, that means that if we have standalone modules with actuators and computation and sensors, then simply by adding more modules to our system, right, then you can add computational power for every new module, right? You can increase the degrees of freedom exponentially depending on how you add them. And you can potentially add sort of sensor networks that span the entire system of the modular robot, right? And if we're even careful, sort of the more modules we add, right, the more adaptable our system here becomes. And if we're careful about the way we sort of implement things, right, then our system can even become robust to individual failures, right? So the collective could simply shed modules that no longer work, for instance, as we've just seen in the talk before this. Okay, so that's my argument for like why I'm interested in multi-agent systems. And I think there's a lot to be gained here, right? Because from very simple individuals, we can achieve a lot. So then why should you care about soft robots, right? That's a little weirder. And I'm going to first introduce sort of briefly the concept of a soft robots for those who aren't too familiar with them. So here's an example of a very simple soft mobile robot. It has these two chambers made of polymer, and it has a backpack with a pump and a valve for each chamber. And the chambers are strain limiting. They have these strain limiting layers on the bottom, and they're organized antagonistically. So if you inflate both of them, the robot will inch forward. And if you only inflate one of them, then it sort of inches forward while turning. And this robot's pretty cheap and modular. You can add more chambers for added payload, right? It's a nice robot. But if we think of it just as a soft robot, right, then there are two components to it. There's a rigid core. Most of it's soft, but there's a rigid core. And the rigid core is really what dominates the robot cost, the fabrication time, the weight, the fragility of the robot. It's the thing that breaks. Whereas the soft part of the robot, right, is fast and cheap to make. It's robust to perturbations. It's multifunctional. So here it's both the chassis or the structure of the robot and the actuator that makes it move, right? But in many cases, in more sophisticated soft robots, you'll see that the soft robot house itself also has sensors and sometimes even control elements. So you get a lot of multifunctionality in these kinds of robotics. So then why make these soft modular robots? Well, as we've just sort of seen, right, soft robots tend to be scalable and affordable with multifunctional hardware that combines, actuators and sensors, and can be robust to physical interactions between robots, which is handy in modular robots because they're operating in very close vicinity. Because it's an emergent field, though, these soft robots tend to be somewhat limited in what they can do, right? So it's typically just a few active degrees of freedom and fairly coarse, noisy sensing. And that's where swarms of soft robots come in, right? So we've just seen that in robot swarms or collectives, many simple agents can coordinate locally to achieve complex emergent behaviors, right? They can pool resources and filter out noise to achieve capabilities beyond the sum of the parts. And we can achieve resilience to individual failures, right? And so I think there's a lot of powerful systems waiting to be explored right here in this space in between these two fields. And I'll give some examples in this talk. But, okay, realistically, having systems with many robots, right, that practically means that we have to place great emphasis on robustness. In fact, it means that robustness, I think, has to be one of the key elements of our entire design process, right? It really motivates this careful co-design of all system parameters that Professor Yim was also talking about. So next, let me skip to sort of our design philosophy and our design approach that we typically take. And then eventually I'll give you some more concrete examples with real robots. So in our design approach, we're actually put sort of system-wide error tolerance over the ability to comply with a particular task. And of course, we design our robots for doing some task, but for them to realistically even get to that point, they have to first work really, really well. Just like survival is at the core of all natural swarms, right? So first of all, they need to be able to survive, and if they can survive, then they can do their task. So our design philosophy, again, is this careful co-design of like fabrication and mechanisms and software, both in operation and control. And I think we can all agree by now that like minimalism is absolute key, right? It means faster and cheaper fabrication. It means less things that break. And that typically, as we've talked about, necessitates very careful hardware, software co-design, and these multifunctional components, because then we can get away with less. It also means thinking about designs that don't necessarily require these tight manufacturing tolerances, because then we can just create more of them faster. To support really large numbers of robots, in terms of operation, we push for mechanical compliance so that they can interact in close vicinity without being damaged, and so that they can link up in these large lattice structures without concern for precise alignment. And we of course need to ensure really low maintenance, right? So you can imagine if you had 1,000 module robot and you need like every module needs like 30 minutes of service every day, right? That's already a full-time technician just working around the clock on these robots. That's not tenable. So, low maintenance, and as part of low maintenance, we also need low wear and tear, right? So preferably as few moving parts as possible. And similarly, we also need really efficient power usage. Or some form of power harvesting. And finally, sort of preferably, right, we incorporate some amount of hardware redundancy so that even if some parts of the system fail, the sheer amount of parts will help overcome that problem. So you can imagine that when you have that many robots, and I think Professor Yim sort of expanded on that beautifully, right? The search space and the planning space becomes intractable very, very quickly. So we need to be clever about the types of controllers that we put in here. We need to be able to very efficiently explore the configuration space, and then also be able to provide introspection to be able to cope with both internal and external changes in our collective. And preferably those control mechanisms could be distributed throughout the modules so that when we add more modules, we don't impede the planning process. I think with the right design, we get lots of redundant degrees of freedom, right? So you just think of that slide mold that I told you about earlier. That's a good thing and a bad thing, right? It means that the search space increases exponentially, but it also means that there are way more solutions to find as long as we're okay with picking some suboptimal ones. And of course, it means that if some modules fail, there are many ways in which the overall system can recover. Finally, we often try to design our robots to be grid-free. And so by that, I mean, like when robots are trying to reconfigure, right, then we don't want to restrict them to these discrete lattice assemblies. Rather, we want assemblies that have many connection points and can stretch and morph and fit into otherwise geometrically sort of incapable gaps. And then finally, and this is probably the sort of maybe the most, contradictory or the thing that people don't so much like to think about is, but I think it's really important that we make all our technology accessible to other researchers, right? And especially because this is such an interdisciplinary space that we actually need lots of minds to work together. And so it's really kind of key to these kinds of complex and heavily interdisciplinary systems. So that means both creating sort of fairly realistic simulation environments, so it's really easy for people to adopt and think about control, but it also pertains to the types of mechanisms we design and the equipment that it takes to produce them. So I think like the key takeaway from this slide, I realize it's a heavy slide, is that I think a dedicated focus on sort of system level robustness over all parts of the complete design cycle really supports sort of truly scalable systems. And in turn, the ability for those systems to then comply with particular tasks, independent of the environment and whatever dynamic task setting we're exposing them to. Okay, So, is there a question?
Maybe you can use the
Okay.
the mic.
Anyways. So you know, up till now, I think my talk has been a little bit abstract. So I'm going to now sort of give you a look at 3 types of deformable modular robots that we published on, and the different types of coordination mechanisms that these support. So in this first example, right, it's going to be operating in the upper left half of my circle here. So I'm going to show you some agents with relatively simple actuation and sensing, but with ample room for intelligence and the ability to, you know, communicate and plan together. So these are the donuts. They're made almost entirely out of flexible PCB. They have 2 8-bit processors that communicate heavily on board. They have IR sensors that are normally located up here on the perimeter, and they have an onboard battery normally. They also have these 12 switchable magnets down here. And then to move, right, they can move on their own because they don't have any actual actuators. But when they couple with others, they can, you know, synchronize their actuation of those magnets and then move together. And they can also use the same switchable magnets to do inductive coupling and then communicate with their neighbors fairly high speed. So you'll see here that it's a flexible PCB, right? So we end up, even though it's very simple, with an easy robot that can morph. And we have demonstrated 3 types of motions that they can produce with each other. So you see one here. This one is actually just sort of like jumping from one connection on a module to another. But there are 2 additional ones here. One is like a gear leg rolling about the neighboring perimeter. That's the one we've used the most. And the other one is sort of it rolls and translates while moving. So there's lots of different ways in which these modules can move by synchronizing what magnets could switch to what polarity when. But I think the important thing here is that because we rely on a flexible PCB as the robot chassis, right, that has several sort of key implications. So we can do really rapid fabrication, right? We get the PCB pre-assembled from some fab house, and all we need to do is really stick on those magnets and then wrap the PCB into a circle. Very, very simple. Very easy to add off-the-shelf components and sensors for further development because it's just a PCB. The low amount of parts and the complete omission of moving parts, right, really lowers wear and maintenance, so that's quite nice. It also lowers the weight and the size of the modules. So an entire module, including a battery, is about 20 grams right now. So it's very lightweight. Finally, right, the flexibility and their ability to passively deform means that they can't just tolerate perturbations, but they can also overcome poor manufacturing tolerances when they're trying to aggregate into large lattice structures. So that actually sort of goes hand in hand with each other. So the first challenge we focused on in terms of coordination was how to get these modular robots to climb sort of light gradients in the environment. And remember, this can be a bit challenging, right? Because we have to reason about how those 12 magnets on every single module lines up with the neighboring modules. So the first thing we did was incorporate this Oracle controller that has complete knowledge of the situation. And it just serves as a baseline for other controllers. So it gives us, you know, an optimal path plan in terms of the number of moves that the collective has to take towards that gradient. But then, of course, next we focus on sort of developing first centralized A-star search algorithms, which can work on board the robots. So the robots are now limited just to the sensor information that they can perceive, right? So the absolute amount of light on each module. They can talk about that, accumulate that information, and then use it, but they don't know what goes on anywhere else in their environment. And of course, it's A-star, it's centralized, it doesn't scale well with the size of the collective, but we showed that it could work sort of on smaller collectives, and that we can tune the heuristic to either promote sort of low energy consumption, where like we have a minimal number of moves, or added redundancy in the connection topology. So again, if some robots fail now, there's a greater chance of system survival, right? That no modules will get shed. We also looked into sort of more naive planners. And in the naive planners, we simply have sort of different versions where we, the modules reach a consensus about which module has the lowest perceived gradient value. And then we move that module closer to the light in different ways. And then we add a bit of randomness to overcome local minima that can occur when we have obstacles in the environment, for instance. And so this latter naive planning scheme is much, much faster, but the plans are somewhat suboptimal. And then finally, we've shown sort of a variety of distributed controllers for example, mapping out obstacles in the environment using either the AIRS sensors on the robots or the connection topology of the robots or strain sensors that are embedded on the robot perimeter. But I think sort of common to all of these approaches is that we're trying to balance computation time, energy consumption, and redundancy in the connection topology, right? That's really what we care about. We don't care about a particular shape. We just care that they eventually reach their gradient formation, and we care about robustness. And so we have to really start sort of exploring what these types of modular robots can do in real life. But I am really excited about applications in these kind of dense cluttered environments where the ability to deform can come in handy, right? So it has to be a smooth surface, but it can be a cluttered environment. So that's my example sort of at the upper left half of my circle. Now the next example, I'm going to focus much more on the right half plane. So very, very simple agents that can communicate only through physical strain and perturbations, right? So it's really sort of exploring where intelligence lives in these kinds of collectives. So in this case, the robots are called the phonebots. They're basically just little soft robotic oscillators. So each robot has a pump and a valve on board that allow the membrane around it to expand and contract. And these expansions are quite significant. So the newest version can expand by up to 185% of its diameter. And the process of expansion, they almost change their overall stiffness by a factor of 2. So like quite significant. The modules also have these resistive strain sensors, so these black lines in their membrane, so they can reason about strain. And they have 6 passive magnets on the side that helps them couple into loose aggregates. They also have neighbor-to-neighbor IR communication, although we haven't actually bothered using that yet because we're more interested in these kind of strain-based coordination mechanisms. So beyond all the benefits that I've already mentioned with respect to soft robots, right? These robots can also be sort of used for things that rigid modules wouldn't be able to do, right? We already talked about how they can change their stiffness, but they're also, for example, gap filling. So if I put them into a space, right, and I inflate them, then because they're just polymer, eventually they'll fill up all gaps, right? And you can imagine there can be sort of applications for that at the microscale, for instance, if I'm trying to block a vessel or something like that. And then we can use, not surprisingly, but it's nice to see that we can also use synchronized movements to have them produce global motion for these traveling phase waves, similar in style to that slime mold that we saw earlier. So again, as with all our robots, we've sort of developed complementary simulators. So we have 2 models that capture sort of the quasi-static behavior of these robots. One focuses on this interplay between the friction and the magnetic and the kinematic forces. And then the other one focuses on how strain propagates within the collective. And so rather than really focusing on traditional high-speed coordination algorithms and systems like this, we're really curious to take these robots down the path of this physical strain-based coordination, similar to what we see in slime molds. Because if we look at strain, right, that's something that comes for free with soft robots. It's what they actuate and it's what they sense anyway. So if we can also use it for coordination, right, that's a free mechanism we get that we might as well be able to exploit. But no one's really looked at how you can exploit strain for these kinds of things. So up till now, we've shown that strain sensing can be used to produce sort of coupled oscillations. That means we can get the collective to either synchronize to do coupled force exertion, or we can have them synchronized with a phase delay like we see in this video to have them move. And then we've shown that we can deploy these consensus algorithms that we're showing in this video, where the robots, even though they really only sense strain on their own perimeter, the fact that they're so tightly physical coupled in this large collective means that they can still reach consensus and achieve, in this case, similar expansion levels if we try to bend it with external force first. And I think there's lots more interesting phenomena to explore in this space, basically, right? Because we see that slime mold can do such sophisticated behaviors, even though they're just coordinating through chemicals and strain. And again, I realize that strain is very low bandwidth compared to Wi-Fi or RF or IR communication, but the beauty, again, is it comes for free with soft robots, right? So you can always use it as a fallback mechanism in case higher level algorithms fail, for instance. So please stay tuned for more updates on that project. So I have one very brief project left I want to mention, and I think my time is up. So this next one is not exactly a modular robot in that it will never have modules physically docked to one another, but they can couple loosely through their local environment. And so I'll show you what I mean by that. So you can think of it still as a modular robot. And what I'm about to show you is a collaboration with the Physical Intelligence Department at the Max Planck Institute, where we're really using a collective of 100 micro robots. So these robots, they're going to respond to a central signal, but because of their morphology and the material and the way they interact for the environment, right? So these free coordination mechanisms over here, we can make them do interesting task-oriented behaviors. So the robots themselves are just these little sub-millimeter scale disks. They're sputter-coated in a ferromagnetic material, and they lie on the water-air interface. And then they're subjected to 2 orthogonal time-varying magnetic fields. So that means that the disks are repelling and attracting and creating flow as they spin around their own axis. And that allows us to exploit both the interplay of hydrodynamic and capillary and dipole-to-dipole interactions to produce interesting outcomes. So I'm showing you some examples up here. And these are, they might look like simulations, but they are in fact videos of the real thing. So again, these robots aren't exactly modular robots, but you can see that their connection topology is somewhat deformable, right? They're also not soft, but because they're sort of coupled in these sort of loose connections that's governed by both the water and the magnetic effects, you can still sort of think of them as a modular robot where we can reconfigure the whole module or the whole system into different shapes. So we've demonstrated 6 modes of operation here, including rotation, oscillation, static collectives, where each particle is spinning around its own axis, static and oscillating chains, and self-propelling particle pairs in these gas-like modes. And I'm showing you some examples here next, where the collective is navigating through an intricate environment. Down here, they're doing contact-based object transport. And down here, they're doing flow-based object transport. And so pretty sort of sophisticated behavior.
Excuse me, Professor Petersen. There's a pop-up window on your screen for the Microsoft Office.
I see it. Sorry. Okay. Is that better? Thank you for letting me know.
Okay, go ahead.
Okay. But so basically you see like a sort of a wealth of different behaviors with very, very simple modules like this, right? The modules, again, like here, there's 0 explicit intelligence. It's all just in the morphology of the robot, but we can still get them to do quite sophisticated behaviors. Okay. So, an example that really lives sort of on the right half side, partially because it has to, right? The robots are so simple now that there's actually no room for real hefty computation on board. Of course, we do have some centralized signal that helps them produce overall coordination. So that was sort of my trip around this circle of different ways in which we can inject intelligence into robot collectives and especially modular robots. And as I said, I think like it's soft robots is such a new area, and modular robots is fairly established by now. There's so much room to explore, and I highly encourage more people to enter this field. It's a little harder because, as I said, soft robots haven't been developed all that far, but I think there's grand potential. And so let me just thank everyone in my group, especially our funding agencies, of course. Stephen Saron has produced many of the soft robots you've seen, Nyla Wilson as well, and Ellie Niles. And with that, I will take any questions. Thank you.
All right, thank you, Professor Petersen. This is a fantastic talk, and it is so inspiring. And I noticed one point is that when people doing soft robots research, they will seldom put the entire controller on their robots. Yeah, but in your soft robot, you are trying to put all the hardware on the robot to make it self-contained, such that it will be more like a modular robot. I think it is. I see this will be quite difficult, especially when you're using some high voltage hardware or anything else. Yeah, but I think it is a very good direction to put all the hardware on a robot to make it self-contained. Yeah.
Yeah, so that's a great insight, a great comment and a good insight that you've had, right? So part of the reason why it's hard for us to use soft robots is that typically in the soft robots world, people kind of take the whole controller and all the computation that it takes and they put it on the side, and then they just have like with one little thin tube going into their actuator. And it works really well. But of course, with modular robots, like we actually want every module, at least to some degree, to be standalone. And so that is a bit of an extra challenge for us.
Yeah, it's a great effort to do it. Yep, maybe we can take some questions from the audience.
Hi, dear Professor Kirstin Petersen. It was a very interesting talk. And I work on the field of robot learning, and I noticed that you have this design philosophy for the combination of the software robots and modular robots in your previous slides. I think it is really hard first to control the software robots using deep reinforcement learning, like using this simulator TaiG. That's for driving the software robots. And then on the other hand, when you have modular robots, then the multi-agent reinforcement learning is also very difficult. Like you have a very large space to search. And now I'm thinking when you combine all of these, and it becomes really, really hard to build an intelligent system. Can you show more insights on your design of the scalable operations and the scalable control? Because these are very important when you really want to make it work with controllers and then the market agent, this kind of planning. So can you talk more about this and maybe show more of your thoughts on this?
That's a fantastic comment. Thank you for giving that. So you're absolutely right. So soft robots are already really hard to model because they have so many passive, infinite degrees of passive freedom. And so people have, they've actually started moving away from theoretical fundamental models and moving more towards reinforcement learning. But now, like you say, right, if you add many of them together, like you sort of have an exponential growth in the search space, and then reinforcement learning can get into trouble. Fortunately, there is nature, right? And nature has a ton of really, it's had millions and millions of years to evolve these kinds of distributed coordination mechanisms. Now, they might not quite be on par with what we're used to, right? They might not have high-speed communication or provable guarantees or anything like that. But if you're okay with sort of slightly suboptimal solutions, there's a lot to be gained there. So there's a ton of distributed consensus algorithms and voting algorithms and quorum algorithms. There's a ton of ways in which robots can act locally, and through that sort of local interaction, eventually produce, at least with sort of reasonable guarantees, some kind of collective behavior. But it does, just like Professor Yim expanded on, right? It does mean that we end up with suboptimal solutions, but they are at least solutions that are robust to failures of individuals and robust to sort of the scaling size. I think there's, especially, and it hasn't really come into play as much in modular robotics as in some other multi-robot systems, but I think often we forget to take into account that the robots are embodied and they do have an environment. And so if they get to actually act on that environment and use the environment, whatever medium they're embedded in, right? It could be fluids, or it could be static, or it could be granular media. If they can leverage that environment additionally to coordinate, right? Actually treat it like a shared memory database. I think there's something really strong to be gained there, but I haven't quite wrapped my head around it. Is that
I
helpful?
think that's a very interesting idea. Yeah.
So we've looked quite a bit at that. Some of the other work we do in our group is on collective construction, and their robots are actively modifying their environment, right? And so they actually treat their environment as a shared memory database, right? They leave cues for each other, and it's sort of a way to create longer lasting signals than having to sit there and directly broadcast what you know.
Yeah, thank you. I think that's made a really good point.
Thank you.
Okay, thank you. Next question. I saw one question from the chat box. Is there a size limit for soft robots?
That's a great question. I think there's less of a size limit actually than rigid robots, right? Because in soft robots, you have a wealth of actuation mechanisms. It can be anything from magnetics or hydrodynamics, or it can be anything, right? And so we're not sort of limited to traditional DC motors and stuff like we are in rigid robots. And the whole philosophy behind soft robots is multifunctionality, right? We embed a whole ton of things into our soft membranes. And so that automatically means that they can scale to smaller scales. So, as you get smaller and smaller, at some point, soft becomes relative. but I think actually the scales of smaller scales in rigid robots do often.
All right. Next questions. Is there any questions?
Hi, Professor Petersen. First, thanks for your wonderful talk. And I'd like to ask some questions. First one, Professor Makim just introduced, in his modular robot, each modular may cost a lot. How much does your soft robot each modular cost? And I think to accomplish a task, we need to use many modulars. And do you have any comments on the total cost?
Okay, so that's a great question. So first of all, I'm not sure it's fair to directly compare the systems because his robots can do much more with fewer modules than ours can, right? Ours are so much simpler that you would need way more of them to do something interesting. But so in terms of the micro robots, since in terms of the soft robotic oscillators, the polymer ones, those are, I think, $25 a piece. And that's just because, the types of valves we use aren't they're not super, I mean, you can buy them on Amazon, but they're not super common. And so because we're not using sort of mainstream components, they're not as cheap. The PCBs that wrap up in a circle right now, they're about $50 per module, but you could probably make that a lot cheaper if you were to order much bigger numbers. Or go to cheaper fab houses. We always on a rush for a deadline, so we order the most expensive ones we can. Does that make sense?
Yeah. Yeah. Thanks for your comment. Professor. Yeah.
Absolutely. But I think soft robots is so much more than pneumatic robots, right? They don't have to just be inflatable, right? They can be any other numbers of actuation mechanisms, and some are much cheaper than others. I'm not a soft robotics expert. I just use what I know from the field to generate, right? I'm actually more of a multi-agent systems expert.
Yes. Yeah. Thank you again. Yeah, Professor.
Good question.
All right. We have one question from the chat box. Is that I noticed that most of your robots move on a 2D plane. Have you considered expanding your work to 3D? And what difficulties and opportunities would that bring?
Yeah, that's a very fair question, right? Everyone wants to go to 3D, of course. So first, two things. The reason why we started with 2D, one is because we're interested in the coordination mechanisms. And so the quicker we can get to a hardware platform that will support developing new coordination mechanisms, the better. And so 2D is easier. But second, 2D actually has a bunch of opportunities. Like if you think of the epithelial cells in your skin tissue, right? Like that's also just 2D, but it's a manifold, and they can still do incredibly sophisticated things like fold, just like we saw the soft robots do. So you have applications where 2D is what we need, right? So if they're trying to move over a surface of an environment or the surface of the water or the surface of an airplane to check out local faults, or generator, right? 2D is totally fine. But I agree, absolutely. I think 3D is really interesting. And so, there are no fundamental limitations to many of the robots we explore and how they would move to 3D. But for the water-air interface, for instance, right, those robots, they only work because they have a surface to move on. For the foam bots, for those polymer robots, I think those have potential to move into 3D eventually. We would love to do it. We haven't done it yet. I need the right students.
Yes, thank you. I think the mechanical design is the hardest part to make it 3D. Yeah. Okay. Another question from Feng Tongji, which is from Chinese University of Hong Kong, and he would like to ask, what are your opinions on the construction of three-dimensional reconfigurable robots, collective robots in a group? Okay.
What are my opinions on the 3D versions?
On the construction of three-dimensional reconfigurable modular collective robots in a group.
I mean, they're harder, right? So I think people like Mike Kim do it exceptionally well. But for many of us, they are somewhat. The problem with 3D, right, is that if I want one module to be able to lift a bunch of other modules, the connection mechanism matters so much more, right? As long as my modules are on a plane, then they never have to lift them. They can sort of move them along or push them, or they can just move on the perimeter and no one ever has to move others. But as soon as I go into 3D, I have to actually lift a whole bunch, and that lever arm becomes really, really hard to reason about. And so not only does hardware get harder, but the the cooperation and the coordination algorithms now have to take into account these effects. And so I think there's a lot of open challenges there. Then again, right, if we look back to nature and you look at fire ants or army ants, right, they just sort of entangle their bodies and they achieve incredibly strong connection strengths, even though they don't have perfect alignment or anything, right? They just sort of entangle. And so there's a lot of research coming out from Georgia Tech, for instance, Professor Goldman's group on entangled robots. And the robots are very simple, right? They just literally flap their wing. They have two wings and they flap them up and down. But because they can entangle more and less, you can still get sort of a very different kind of modular robot, but it is technically a modular robot. And it's similar to those fire ant systems we see in nature. So maybe that's the right direction to move in eventually, if we're okay with these sort of more amorphous style solutions than we've seen in the past. Hopefully that sort of answers your question.
Okay, good. And all right. And another question is it meaningful to study swarm bots like kilobots? Any good suggestion?
Specifically for the context of modular robots. Kilobots is a fantastic platform. So Professor Rubenstein was one of my lab mates back in the day at Harvard. And it's they're very eye-opening for all of the hardware problems that we encounter, all of the realistic problems we encounter when robots are actually embodied in real life. And I think, before they existed, we kind of thought about them, but software engineers didn't really appreciate that they existed. And people who hadn't done it didn't really appreciate the full scope of challenges that it involved. So, and that means I think kilobots are incredibly powerful and valuable to look at. That being said, of course, they're completely stuck on a plane. You put down a piece of paper, they can't move over it, right? And so I think maybe for modular robots, they might be it might be harder to gain insights. Because again, we're all arguing, right? Co-design is so important. And if, the mechanisms from kilobots never really scale to these kinds of things. If you do look at the more recent work from Professor Rubenstein's lab, right, he has these robots that are actually called fire ants. I think because sometimes they catch fire, I'm not sure. But those can actually climb in 3D. And those are, incredibly powerful modular robots. So I'm really excited to see what comes of them in the future.
All right, thank you. We can take one more questions.
Hi, Professor. Can you hear me?
Hi.
Thank you for an inspiring talk. I was one of the reviewers of the Boombox paper, the IL paper. I was very impressed with that paper. Soft robotics is a hot topic. Modular robotics is another interesting topic. And the combination of these two, wow, what a great idea. And I'm glad to have the opportunity to continue to learn about this work today. Professor, we know that the modular and soft robotics both have we know that modular and soft robotics both have promising application in their respective fields. Do you ever consider what surprising applications such as soft and modular robots could have?
That's interesting. Things that you wouldn't have thought about beforehand. I mean, in my mind, modular robots are already so futuristic. It's hard to imagine what they can't do. I think my eyes are opening more and more to the micro scale, right? So once we start thinking about modular robots that can actually interact with cells or surround cancer cells or, start doing things at the micro scale, I think that's really, really powerful. I don't know if it's surprising, but it would be pretty exciting development in the future for sure. I think one of the things that surprised us the most is just how powerful the strain-based coordination may be. is, you know, it seems so simple, but there's like a lot. It turns out there's a lot we can do in that space. And so I think often, you know, we tend to forgo the low-level coordination mechanisms because we have high-speed communication and really good planners, and computation is cheap these days. But there's really no reason not to explore both, right? Because they can complement each other and they can live on the same robot, and one doesn't hinder the other. So I think there's a lot of exciting stuff there. Does that answer your question?
Does it answer your question? Okay. Okay, good. So I think it's time to wrap up. And again, I would like to thank you, Professor Kirstin Petersen, for your fascinating sharing. And I love your talk very much, and I hope all the participants will enjoy it too. Thank you very much.
Thank you.
All right. Next Tuesday, we will have another 2 top scholars in this area to give a talk at 3 p.m. Please stay tuned and welcome to join our events. See you next week.